Okay, hi. Welcome to this week's lesson. So just a reminder, the last few weeks we've been looking at the way that heat transfers. We've looked at heat travel by convection. So remember, this takes place in a fluid, that's a liquid or a gas, hot fluid rising, cold fluid taking its place. And we looked at various examples where that happens. Yeah? So be aware, these are the sorts of examples you might be asked about in examination questions. Okay, we looked at heat transfer by conduction. Okay, so the vibrating particles colliding with each other and passing the vibration along. We talked about metals being good conductors because the atoms are close together and they have free electrons that can jump from atom to atom. And we talked in particular about gases and air being bad at conducting, i.e. they are insulators. And remember, we answered lots of questions that relied on the fact that trapped air is a good insulator. Okay, and finally we looked at heat transfer by infrared radiation. Remember, that's an electromagnetic wave. It can travel through a vacuum, etc. And remember, we learnt that black objects are both good absorbers, but they also emit, they give out infrared radiation when they get hot. And the opposite is true of shiny or white objects. They are poor absorbers, and hot, shiny or white objects are poor emitters. Okay, we're going to move on today. And we looked at examples of using them. So we looked at loft insulation, trapping air to stop heat being lost from a house. We looked at cavity wall insulation, the same thing, stopping heat escaping from a house. And we looked at our vacuum flask. Okay, so remember, the stopper stops heat escaping by convection. Okay, in the double-walled flask, so here there's a double-walled flask, it's got a plastic container. The actual vacuum flask itself here has got a vacuum in between the two layers, okay, which stops heat escaping by conduction because there are no particles to vibrate. Remember, both the inside of the flask and the outside of the flask are shiny, so they reflect infrared radiation. Like I say, normally these vacuum flasks are quite fragile. They're put inside a plastic case like that, so you don't actually see the vacuum flask, the shiny vacuum flask inside. Okay, so today we're going to move on. So just a reminder then that the energy, whether it's kinetic or thermal or electrical, whatever, we cannot make it, we cannot destroy it, we can only transform it or change it. Okay, and remember, energy is measured in joules. Okay, now, this lesson we're going to look at work. Now, as in many words in English, a word has a different meaning depending on its context and its subject. So, for instance, decay has a different word in biology, where a body will decay, whereas in physics, when we talk about radioactive decay. And the same is true of the word work. In physics, as it says on the slide, work has a very special meaning that is different to normal English. In physics, work is the amount of energy that's transformed, changed, when a force moves in the direction of the force. So what I'd like you to do is to pause the video, and if you could copy this into your books, please. Okay. Now, the key thing there is the force has to move in the direction of the force. So when you're carrying the shopping home, okay, you're using a force to lift the shopping, but you're not moving in the direction. So I'm going to try and show you that. If I put my camera on so you can see me. Okay, so I'm going to go and pick up my trumpet case. Okay, now when I pick the trumpet case up, I am doing work because the force is moving in the direction of the force. I don't know if you can see the arrow. I've shown it white. Okay, so that arrow. So when I lift it up, that force is doing work. However, when I walk with the case, okay, well, I'm moving in this direction, but the force is in that direction. So this time, this force is not doing work. The force actually has to be moving in the direction of the force. So when I pick the case up, I'm doing work. When I move in this direction, I'm not moving in the same direction of the force, so I'm not doing work. That's quite tricky. Those of you that are doing A-level physics will talk a little bit more about that. Okay, so let's go back to the PowerPoint. Okay, so just be aware of that. Okay, so here's an example. There's Mr. Porter. I'm going to push a table across the floor. I won't go onto my video to show me doing that. You can imagine me doing that. So I'm using a force and I'm moving in the direction of the force. Now I can calculate the amount of work that I've done, how much energy is transformed. And all I have to do, this is the wonder of physics, is I just multiply the force, measured in newtons, by the distance, measured in meters. And if I multiply those two numbers together, that will tell me how much energy I have transformed, or energy I've changed. So we've got a little formula here, another formula to learn. So again, if you can pause the video, if you can copy this in your books. So the formula we're going to be using this week is that work, the amount of energy that you've changed, is the force times the distance. Force has to be in newtons, the distance in meters. So just pause the video and copy that down. Okay, so we can have a look at an example here. Here you can see a man doing a lot of work. He's doing a big force because he's going to pull a bus. And the amount of work he will do is going to be the force multiplied by the distance he pulls the bus. Okay, so here's a nice simple example. A woman pushes a car with a force of 400 newtons for a distance of 15 meters. How much work has she done? Okay, so we know the force, we know the distance. Okay, we write the formula down, work equals force times distance. We put the numbers in, so the force was 400 newtons, the distance was 15 meters. If the distance had been given in centimeters or in kilometers, you'd have to change it to meters. And you put it in your calculators, 400 times 15 is 6,000 joules. So the woman has transformed 6,000 joules of energy. So that will be chemical energy in her body converted to kinetic energy, something like that. Okay. Now, of course, when we lift objects, we're using a force, and there's a distance. And, of course, the force we use is just the weight of the object. Just remember, weight is a force. It's measured in newtons. Okay? So the lifting force is equal to the weight of the object. That's how much force we've got to use to get the object to move. Okay, so a nice simple example. A man lifts a mass of 120 kilograms. Notice what I did there. It says mass, not weight. To a height of 2.5 meters, how much work did he do? Well, first of all, we need to find out, well, what force did he use? What is that weight? And if you remember, weight equals mass times gravitational field strength. On the Earth, the gravitational field strength, G, is about 10. So if the mass is 120 kilograms, the weight will be 10 times that. It will be 1,200 newtons. Then we can just use our formula. So work is force times distance. We've just calculated that the force, the weight, is 1,200 times 2.5. So he's done 3,000 joules of work. Okay, now if this was the lesson, we'd actually do a little bit of lifting ourselves now. We'd do some arm curls. So we'd get some barbells from the gym or some kilogram masses. Okay, and we'd do some arm curls. Of course, the force would be the weight of the object. So if we used a 1 kilogram barbell, that would be 10 newtons. And the distance of an arm curl, of course, is from the bottom to the top, as shown on the diagram. And I'd get you all to do that, to calculate how much work you did in one lift, and then we'd see how many lifts you can do in a minute to find the total work. It's normally fun to do that, but I don't think there's a point of you doing that at home. Okay. And with this lesson, there is a worksheet. It's called Work. Uses the formula that we've been using. Okay, so it uses this formula. And again, if you can answer the questions on the Word worksheet, and if you can upload it on Share My Homework. Okay, thank you.